Welcome to Pomodoro Joe for Sunday, July 2nd, 2023. Today we're doing LeetCode problem 1601, maximum number of achievable transfer requests. This is a hard problem. We have n buildings numbered from 0 to n-1. Each building has a number of employees. It's transfer season, and some employees want to change the building they reside in. You are given an array requests, where requests index I is equal to from to, represents an employee's request to transfer from building from to building to. All buildings are full, so a list of requests is achievable only if, for each building, the net change in employee transfers is 0. This means the number of employees leaving is equal to the number of employees moving in. For example, if n is equal to 3 and 2 employees are leaving building 0, 1 is leaving building 1 and 1 is leaving building 2, there should be 2 employees moving to building 0, 1 employee moving to building 1, and 1 employee moving to building 2. Return the maximum number of achievable requests. And then they have some examples. All right, so the basics of this one. We have a number of buildings. Each one is at maximum capacity for employees. Now, some employees want to transfer to other buildings. In order to achieve these transfers, you have to strike an equilibrium between all the different transfers that happen so that all the buildings end up with the maximum capacity again. All right, that's pretty straightforward. And they have some constraints. Okay, I actually think this one doesn't sound that bad. All right, let's set 25 minutes on the Pomodoro timer and we will get started. So for this, we have n buildings and requests, lists of requests. All right, so at the beginning, we'll have some result, set it equal to 0, and we'll return the result at the end. Now for this one, I think I'll do a recursive solution. And the reason why I'm doing a recursive solution is this one is actually fairly binary. You have two options. For every request, you either do the request or you don't. That's pretty much what it comes down to. So we'll have a recursive solution that goes through and tries every option where we either do the request, or I should say we both do the request and we don't do the request. And then we just choose whichever one of those options gives us the better answer. All right, so for this, we'll start with some basics. I'll be building this up from the fundamentals, so we'll just start with a framework here. All right, so we're gonna start with a function, maximum request recurse. And for this, we do need to know which request we're processing, so I'll have the request index. We might need other information here, but I'm gonna skip that for now. We'll also need to come up with our base cases. Again, well, we'll do one base case now, and then we'll have other base cases we'll have to handle later. So if this request is at the end of our request, if this is outside of the bounds of our requests, then we're done. Actually be greater than or equal to the length of our requests, then we're done, and we can return 0. We'll probably come back to that later, but this is our base case. Okay, so we have our base case. Now, what are our other cases? Well, we have two options. We either do this request or we don't. So option 1, we'll do the simple option first. Don't do the request. So I'll put a note here. All right, so for option 1, we decide not to do the request. So in that case, we just do a recurse call on the next available request. So we don't do anything, we don't do this request, we just go to the next request. All right, so that's option 1. Option 2, we do the request. Interesting. So this is going to be also request plus 1. So how do we actually do the request? Well, that's going to take us to the next part of this puzzle. So to do this request, we actually have to get the from and to, and we need to update some state where we actually take an employee from their building, from building, to the building, to building. Okay, so for this, we'll pull out the from and to, and then we'll talk about the state. So request from and request to. Let's see, is that right? Yes, this is from and to. So the request from and the request to is just the requests at this index. Okay, so now that we have the from and to, how do we update some state? we need some buildings where we actually move the employee. So let's talk about this a little bit. I'll come up here and do some diagramming. So initially we have some buildings and they have some people, 34 or 23. We don't really know how many people are in each of these buildings. So let's just have some diagram here. So this is building 1 or building 0. Building 0, building 1, building 2. All right, so in each of these buildings, we have some number of people. That's the max capacity, but we don't actually know how many people. So the key here is to keep track of not just how many people are in the building, but how many people there are offset from our equilibrium. So initially, we don't know the number of people, but we know that when we move one person from building A to building B, so let's say we go from building 0 to building 1, well then building 0 has a -1 from their equilibrium, and building 1 has a +1 from its equilibrium, and building 2 has a 0 offset from its equilibrium. So essentially we'll fill this array. We'll have an array that represents all the buildings and their offset from their equilibrium or from their base state. Now their base state, we don't know how many people there are, but it doesn't really matter. We just need to know how far away they are from that base state. So when we move a person from one building, we'll take one person away from their base state. And when we move a person to a building, we'll add that person to the base state. So this is their surplus or deficit of people. All right, so in this way, we're able to go through and try our transfers without actually having to know how many people are in the building. Now, once we reach a new state, where all of these are back to 0, we've reached a new equilibrium. All the buildings are in balance again. At that point, all the transfers that we made up to this point are valid transfers. It means we've able to use all these transfers to balance out again, and we've reached a new balanced state. At that point, we can lock in those transfers or those requests and keep that number of requests as a valid set of requests. So let's do this. So now instead of just taking in the request index, we'll also take in some state. Okay. And let's see, down here, when we make our initial call, we'll need some state. So let's set our state. So we'll have a 0 balance for all of our buildings. So essentially every building is in balance. All right, then we'll make our call. Let's see, what else will we need to pass in? Well, at this point, we also need to pass in how many of our transfers have we done? Because we're not keeping track of the actual transfers. We just need to keep track of the count of transfers. So we'll keep track of how many transfers have we done up to this point. And if we reach a point where all of our buildings are in balance again, we can actually lock in this count as being valid transfers. So let's do that first, actually. So we'll have some internal result here. It's going to start at 0. Then we can check, is our state balanced? So maybe we'll have some function for that. Maybe I'll call it is valid end state. How about that? We'll pass in our state. And if this is a valid end state, then we can lock in all of these counts, all of these requests that have occurred up to this point. So our result will actually equal this count. And then we can reset our count. So essentially, we're going to keep track of how many requests have we made and transferred, done these transfers. Once we get to a count that's valid, or we reach a valid state where we have balance with all of our buildings again, our result will be that number of counts. That is our base number of transfers that were valid. And then we can reset our count to 0 because we're basically starting this entire problem over from this request index to the end. All right, so we do need this function. Let's create that out here. All right, so now to check to see if this is a valid end state, we basically have to just go through and make sure that all of our buildings have a 0 offset from their equilibrium. All right, so for building or balance in our state, if that balance isn't 0, then this is not a balanced state or a valid end state. Otherwise, if we make it through all of our state, all of our buildings, and everything is zeroed, this is valid, so we can return true. Okay, back to our main part of the problem. We'll check to see if we have a valid end state. If we do, then we'll just lock in all of those transfers that we've done. That'll be our base result. Otherwise, we'll move on with our current result, which is 0. All right. Then we have our base. Now here, instead of returning 0, let's return our result, because we might have locked in some valid requests. So let's return our result here, which will either be 0 or this new valid base state count. All right. Still go down to our requests. Oh, but here we need to pass in our state. Now our state doesn't change and our count doesn't change. So those are exactly the same. This is if we don't do the request. We just go to the next request with the same state and the same count. Now if we do the request, we didn't actually address this yet. We've pulled out the from and to from this request. Now we need to update our state with these new values. So our state, let's see, we actually want to make a copy of our state. Because this is a list and it's a reference variable, we will need to make a copy of it so when we make changes to it, we're not impacting all the other recursive calls. So we have some new state. This might be expensive, so we might have to address this in the future. Let's just try this for now and see if it works. So we'll make it a copy of our state. Then in our new state, let's see, our from, let's see, request from. So this building has one person leaving, and the new state request to has one person entering. All right, so we take one person away from the from building and we add one person to the to building. So then when we do our recursive call, we pass in this new state and we've done one request, so we can do count plus 1. All right. So we don't do the request, we just pass our state and count through with the next index. If we do the request, we have to update our state, make a copy of it first, pass in this new state with one person less from the from building, one person more to the to building, and we update our account. Now out here, we'll want to return whichever option gives us the maximum number of requests that we can perform. So we'll return, let's see, the max of option 1 and option 2. Is that right? Not exactly, because we still have these results here. We might have some count that we've already locked in, so we actually need to add our result to this. Result plus the max of option 1 or option 2. All right. So this should take care of our recursive function. Now out here, we do need to make our initial call. So this external result here will be maximum number of requests to recurse. We'll pass in the 0 for the start index. We'll pass in our initial state, which just has zeros for everything, and initial count as 0. At the end, we'll return our result. All right, so I think this should handle it. Let's give it a shot, see how many typos I made. And I didn't make any. We pass. All right, let's submit this and see if we can pass all of the tests. And we pass. And we do okay. We beat 50% for runtime and 33% for memory. That's not too bad. So one thing we could do, let's jump back here. So if you remember yesterday's video, or if you watched yesterday's video, you might have noticed we did something very similar to this, but we used something called backtracking. That's where we kept one state, one global state out here. We essentially performed this step where we added the people to the buildings. Well, in that case, it was cookies, but you add the people to the buildings, you do your recursive call. Then after your recursive call, you reset your state so you can make your next recursive call. So we could do something like that here. Instead of passing a new state all the way through, we could keep one global state. That might save us a little bit on memory, and it even might save us a little bit of runtime because we're not making these copies. We can give it a shot. It might be a little bit more complicated than this, so I don't know if this is going to work, but we got a little bit of time. Let's try it. So we'll have one global state. Actually, I'll just grab this. All right, and we should even move this to the top so I can use it everywhere. Well, no, it's fine. It'll be fine. So now instead of passing state in, we have our one global state. We can get rid of this and this. So we're not passing state anymore. We're just going to use the global state. Now this new state, we don't have this new state anymore. So this is going to be global state. We'll do update on the global state. We'll call this recursive function. Then we have to go through and fix our global state back up after we do the recurse. So now we come back here. And this global state, instead of subtracting one from the from, we'll have to add one back to the from, and we'll subtract one from the to. Okay, so this is keeping one global state instead of having to copy the state every time. Let's see if I missed anything. I think I got it all. Let's give this a shot. All right, so this I have to pass in the global state. All right, try that one more time. So this works. Let's see if this saves us anything in terms of runtime and memory. I bet it saves memory. I don't know about runtime. We'll find out. It actually does worse in runtime, 49% for runtime, down from 50%, so tiny hit in runtime, but up to 53% memory, that's up from 33%. So small hit to our runtime, but significant improvement in our memory. So it's a decent trade-off. I don't really like using global state like this, just because globals generally give me an icky feeling. I don't really like globals. So I wouldn't necessarily recommend this, but I just wanted to show you how you can do it. All right, there are things we can do in here to clean this up. See if you can gain a little bit more in this runtime. I mean, 50% isn't bad, but there's a lot of room for improvement on this. I think one thing we can do for sure is move this function call just into here. This code is pretty simple. You could easily move it in here and save yourself a function call. So that's one thing we can do. Anyway, I think that's it for me. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can try this one on your own. This one is 1601, maximum number of achievable transfer requests. It's on the easy side of hard, so check it out. All right. Hope you enjoyed this. Hope you learned something. Hope you had fun. Hope you can go out and write better code.